All right, I'd like to welcome everyone back for our next speaker. Dorit, if you, do you want to go ahead and share your slides?
There we go.
All right. So our next speaker is Dr. Dorit Hammerling. She is an associate professor of applied mathematics and statistics at the Colorado School of Mines, and today she'll be discussing machine and statistical learning fundamentals. Thank you,
All
Dorit.
right, thank you for the introduction, DJ. Yes, a little bit more about my background. I used to work in automation and IT, and then got a PhD working on spatial statistical methods, specifically for satellite data, and then worked a lot in the analysis of massive data. I worked at Anchor for 6 years, and like DJ said, I'm an associate professor now at in applied mathematics and statistics, and I mainly teach our graduate level data science courses, specifically the statistical learning sequence. And one thing I'd like to say, given some of the questions I saw, the kind of the direction we follow now, all our data science master students, they follow a dual track. That means we are trying to get them bilingual in computer science and statistics. They take a course sequence, a 6-course sequence total, where 3 on computer science, so viewing machine learning from a computer science angle, and then an analogous sequence where we go through statistical learning methods. And we also train all our students to use both R and Python, and there's a good reason for that, because often the statistical community, if the advances in methodology, it takes a few years before they make it into Python, and they're usually maybe not as well implemented, so there's some purpose in being very familiar with R. And the same with Python. There's obviously amazing tools, especially if one of the things that DJ was talking about, the X-array tool set. There's wonderful things to do in specifically in applications in earth science. So you really want to be familiar with both of these tools here. In terms of my talk here, I'm going to have 3 blocks, and I'm going to field some questions after each block. So in about 15 minutes, I will take a break for your questions. We don't have that many questions only at the end, and you get a chance to ask questions if there's something that isn't clear here. So we'll get right into it here. So there are 2 useful reference books here that are both free and very well written. You can really use them for self-study. I will draw from these books. The Introduction to Statistical Learning is a little less mathematical. The Elements of Statistical Learning is a higher advanced mathematical level, but both very readable. They have code examples in there, and they're really useful for self-study as well. Especially the book on the left, there are lecture notes by some of the authors and videos that you can use, so ideal for that. All right, with that, jumping right into that. So I'm going to use the term statistical learning and machine learning somewhat analogous, viewing that in statistical learning, there's a bit of a different conceptual way of approaching this, the methods, but overall, they're actually very, very similar. So I think it's valuable for you to be familiar with both of these perspectives here. So when we talk about statistical learning, we talk about a very large set of tools to go on insights from data. So DJ has already mentioned a few of them. Deep learning would be an example. Linear regression is another example that's maybe on the much simpler end here. When we categorize these models, the highest level categorization is supervised versus unsupervised learning. And what we mean by supervised is that there is a concept of an output. So something that we're interested in learning more about, and we do that as a function of one or more inputs. Classical examples for that are classification or regression. If you're wanting to know, will there be a hurricane, or how strong will the hurricane be, and you want to do that based on other inputs, these would be examples of supervised learning. Unsupervised learning is when we don't have an output, but we only have inputs. The idea is that we really want to learn more about the structure of these inputs. Examples of that type of analysis are clustering analysis, association analysis, a lot of that, what you might be familiar with, graphical models, where you're really trying to understand the structure within the data. Dimension reduction, principal component analysis, that's our main go-to that had already been mentioned before. It's another example of that as well. If you have very high dimensional data and you're bringing it down and you're seeing what is the structure in a lower dimensional space, you use tools such as principal component analysis. I'll focus on the supervised setting for the rest of the talk. So again, the supervised setting is where we have a specific output. That's our main interest. And we have one or more inputs that we want to use to learn more about that output. So in it, I'll keep the math very low here, but it makes sense to have some very simple equations there so you can conceptually talk about things here. So the idea here, y is the output that we are interested in, and x are all the potential inputs, the variables that we have available that help us to learn something about y. And f here is a very, at this point, very unspecified functional form that relates the x's to the y. And if you think about this in a statistical framework, we also have this epsilon there. And what that epsilon refers to is a random error term. We'll clarify that a little bit more. But the idea is there's some kind of error that we can do nothing about. We'll refer to it later as the irreducible error. So having that conceptual framework in mind is useful. And our main goal here in this type of analysis is always estimating f. That means we're trying to see what can we do to relate, or what's the best way to determine what that function that relates the inputs to our output is. Going back here, there's one other term I would like to clarify, because a lot of the literature uses this categorization, and this is the categorization of regression versus classification problems. That refers to the nature of the output. So if our y is a quantitative variable, that means it's a numerical variable, that is a regression problem. Let's say if you're interested in how much will it rain, assuming we have the condition that it will rain, you're interested in how high is the amount of rain or precipitation that we will see, we would address this as a regression problem. In the other case here, if you're asking the question, will it rain? Will we have a hurricane? So in our case here, the output is a qualitative, a categorical variable. This is a classification problem. This doesn't just need to be a binary variable. This could be many levels. For example, if you say, if we have a tropical storm, or if you have a hurricane developing and we are interested in will it be a class 1 or a class 2, a class 3, a class 4, a class 5, this is still a classification problem. The input variables, that's often confusing to people. The nature of the input variables doesn't matter. So some of the inputs can be quantitative, some can be qualitative. It's only the output that matters. So you can have a regression model where some of your input variables are of qualitative nature. For example, one of the typical ones used in Earth system science is that you use season. Whether winter, summer, spring, fall, that would be a case where you use a categorical variable as one of your input variables. In this setting, there's also a bit of a gray area here, because, for example, if you think about logistic regression, so logistic regression is a modeling framework where the output is binary. So in this case, our output is categorical, but we still call this type of model regression. So it's good to keep that in mind, that this isn't exactly a black and white line in terms how these terms are used here. So when we want to estimate f, so now we are after what is that function that relates these inputs to the outputs. There are two main reasons why we want to do that, what our motivation for doing this in the first place is. One is prediction. That means if we get a new set of x, what will y be? So if you're interested in, let's say you want to see, will we have a tornado forming? That's what you're interested in. This falls in the realm of prediction. A different approach here is inference. And what we mean by inference is specifically what is the nature of the relationship between x and y. This might be that you're not worried about doing any kind of prediction, but you're trying to understand how is x and how are x and the x's and the y's related. And the reason you want to keep that in mind before you approach that is what your ultimate goal here is will really define what choice of model for f you use here. And on a very high level, you can think about there's a big trade-off between prediction accuracy and model interpretability. And typically, the simpler, and simple is analogous to saying a model is less flexible. So the simpler model is that generally it is much easier to interpret. If you think of a classical example, if you have a linear model where you have two outputs relating to one input, it's very easy to interpret this model. It might not be a good model, but purely from an interpretational point of view, that's an easy model. On the opposite of this, and there has been very good research to kind of counteract that, but deep learning models that have a lot of parameters, it's much more challenging to directly interpret what the relation to the input to the output is here. I think tomorrow we'll actually see examples that show other that this is actually done, but in general, I think this is a correct way to think about it. Is the simpler model is, the less flexible model is, the easier it is to interpret. So when we think about the prediction equation here, is what we do when we predict is we determine what our estimated y is using the estimate of our functional form. Again, we haven't discussed what these functional forms can all be. We'll do that soon here, but that's the general framework how you think about prediction here. So we use that functional form, that f hat. So in statistical terminology, and that's probably useful for you if you read the literature, that hat, so that little kind of hat on top of the y and the f that always refers to an estimated quantity. So f hat here is the estimated function relating the x's to the y's, and y hat is the prediction of y. And if prediction is our only goal, then f hat can really be treated as a black box. In this case, we are not concerned with what are the details that go into f hat. So maybe as a developer, you're interested in that. But if you're a user, you really don't worry about that too much. All you care about is how accurate your predictions are. And on the next slide here, we'll talk a little bit about what we really mean by prediction accuracy. That seems very obvious, but there are actually different ways of measuring that and a lot of details on how you truly assess that. On a high level, you can think about prediction accuracy as a measure of how close is our estimated y hat to the true y. This is usually expressed as the square difference, so between the predicted and the true value of y. And so you can see this here on the left-hand side. So there's so the difference here is y minus y hat. So the true y minus the estimated y squared. There's some statistical terminology in here. This E, that capital letter E, stands for the expectation operator. And in statistical terms, that means what is our expected square difference between these two values. In statistics, we think about these components decomposing that. And what you can see here, if you plug in what our expression for y is as f of x plus epsilon minus our estimate of x, where we don't have the epsilon term anymore, and then you group them differently. On the left-hand side here, you get the so-called reducible error. And the idea behind the reducible error is that if you had a better model, you can potentially bring this error down to 0. If you have the perfect model that exactly corresponds to the truth. The right-hand term here, the so-called irreducible error, is that term that corresponds to that epsilon. And that is a term that conceptually we cannot get rid of. And we'll talk about this framework a little bit more after an illustration here. So I'm using all the figures from the statistical learning book for illustration, which again is freely available. So if any of this interests you in more detail, you can just look this up here. But I'll walk you through this quickly here. So any example here, so we see here an artificial data set showing income, so how much money you make as a function of years of education. So I hope that all motivates you to go to grad school. So you can see in the simulated data here, we have a clear upward trend here. On the left side, you just see the data. So that's what you would be getting if you work with it. On the right-hand side, we see in this specific case, because this is actually an example, an artificial data set, so we know what the true function is here. So the true function here is that blue line. And these thin vertical black lines are the error terms. So this is, we have modeled from this true function, but then we add some error where we assume there's just some variability. Even people who have the same years of education, they don't exactly make the same amount of money. So that's conceptually what the irreducible error is. If you think about your applications, there might be values that there's measurement error, your system, you might not have all the access in your model that explains it. It's very hard to think about any kind of practical application where there isn't some amount of irreducible error that's in the system. And keeping that in mind is very important, because you don't want to spend a lot of time trying to chase something, and that's where we get in that regime of potentially overfitting, where we start fitting to noise. So having that framework in mind, that there is a part of the error that we can reduce and a part that maybe really forms an upper bound of how well we can do, is important here. So statistical learning focuses on minimizing the reducible error. For the irreducible, this is not done. So it provides a bound for the prediction accuracy. And I'm going to talk about, so the concept of irreducible error is conditional on which variables X we have. If you think about that formulation back, so f of X, if we have a different X there, the amount of irreducible error might be different. For example, if you have a model where you only include one potential input variable to explain your output compared to a whole set of prediction variables that might truly be related to your output, then what your remaining error is might be quite different here. So in a climate model, there's also that aspect about inherent variability in the system model. I think many of you work with climate models, and I've certainly worked a lot on that concept that you start off with changing the initial conditions, and then you get a so-called ensemble spread. That means there's some variability in the system that has nothing to do with actually some forcings or actually what you're interested in. Well, let's say if you're interested in modeling how temperature behaves as a function of how much CO2 emissions are put into the system. There's a relationship there that you are trying to get at, but there's also a component of variability. If you had just done some tiny perturbation in the system, because we are dealing with a chaotic system, if you had done a tiny perturbation in the system, you'll get different amounts of variability. So what you are after is you want to understand, how can I estimate the functional form that really relates my CO2 to my temperature, but you're not trying to fit all the noise that comes along with the fact that we're dealing with a chaotic system. All right, so now switching gears, if our main interest is not prediction, but rather inference, so I'm just gonna repeat that again. So we want to understand in this case the relationship between the X's, and this is, you can think about X as being a matrix of different input variables, and our output of interest Y. We're specifically interested in how does Y change as a function of these different X's, or inputs. So in this case, we don't want to treat that F hat as a black box, but we are really interested in its exact form, because we're trying to answer questions such as these ones here. One of the things that a lot of analysis in both actually the machine learning and the statistical learning context is focused on is you want to select which variables, which of your potential inputs are actually related to your response. If you can think about, if you're interested in predicting, let's say, hurricanes, you're interested, and you might have literally 80 candidate input variables that might help you explain something here. The question is, do you really need all of them? And which of the ones can you are truly useful to explain your response? This is a case of variable selection. There's a lot of analysis, if you do this type of careful analysis, is exactly spent on that, finding out what are the inputs that are relevant. And once you have that question answered, the next question is, what's the nature of the relationship between the predictors and the response? And that's where we get into model selection. Again, to use these extreme examples here, some modeling frameworks might do very well with a linear relationship or extensions of it. for some problems, you might really go all the way and use something like deep learning that's highly complex because the relationship truly is so complex and you can capture a lot more regimes. You want to keep this in mind on a high level, and when you investigate and work with your data, think about where does your problem fall within this scenario here. In many practical scenarios, we're actually interested in both, in prediction and inference. That's then more where you need to kind of weigh what is then, that's why it's so exciting to see all the new work in deep learning where we really have interpretable deep learning methods, which is something that wasn't really on the radar, let's say 5 years ago. All right, with that, I'm gonna do a little question breaks here. So we'll take a few minutes for questions in case you have some now. All right, can you elaborate more on reducible and irreducible error? Yeah, I can try. So the idea is reducible error is the error that results from the fact that our model isn't quite good enough and the true relationship between the input and the outputs that we have available isn't characterized well enough. For example, in that simulated data set where we saw the income versus years of education, if you had just fitted a linear straight line through that, this would not have been a very good model. That would be the case where we still have a chance of reducing the reducible error. The irreducible error is conceptually an error we can't do anything about. There's something in the system, that would be the chaotic behavior and climate models, we just can't get at it because it's nothing that we have available to us. Most chaotic systems are truly characterized by that. That means very, very small changes lead to different outcomes. In this case, the best thing we can do is characterize the distribution of a prediction at a given value. So Emily, let's see, how inherent variability versus when we are missing a potentially useful input variable. So that's a really good question. So the question here is, how can we differentiate between inherent variability versus when we are missing a potentially useful input variable? We don't know this for sure, but one way to tackle it is you try to get your hands on every possible input variable and you perform these variable selection techniques. And in what you do in variable selection, you basically look at, does my model get better if I include more variables? And they're based to account for the fact that you just have more variables. We literally teach a whole class about that. That's a really good question. So that's the way to do it. You use all your potential input variables, and if you don't see any improvements anymore, then you kind of call it quits and say, yep, that's probably it. Seasonality in regression problems, for example, predicting, yes. So that's, actually, in my example, we'll talk a little bit about that. So when you think about regression, seasonality usually refers to the fact that there's some inherent seasonality in the output that might not be your primary interest to model. One approach to doing that is correcting the output immediately, where we fit a functional form to the seasonality and then work only with the residuals and then model the residuals. Another way to go about that is that you can specifically include seasonality as a term. In this case, you would use as one of the inputs a qualitative variable that contains whatever, let's say winter and summer, if you're only interested in these two seasons. And that allows you in that relationship to have a different model for these two. All the other terms are still the same, but you can build in seasonality and you can use things such as interaction effects. So you can actually see how season might influence the effect or modulate the effect of some of your other predictors. Also, the expected value. Okay, so the expected value is a mathematical operator in statistics that takes that is a constant if you put in a constant and uses the mean value if you have a random variable. That might be a little bit of a loaded question here. If you look it up, expectation operator, there's really good literature on that. It will take you about 20 minutes to understand it. If you find him, yeah, so that question about correlation versus causation, that's a tricky one. Yeah, all these kind of relational frameworks, there's nothing that we truly do about causation. There's a whole class of models called so-called causal inference. And what you do in this causal inference scenarios, you actually run experiments where you modify some of the inputs. So in this specific, none of the things we talk about goes after that. Yeah, so that we really don't address this question here. How are you defining regimes? I don't remember saying that word, so I would have to guess on that. Kylie, if you can clarify what you meant by that, I might give a more useful answer. Usually it's some way we use the term regimes is that if we believe that the relationship works differently under certain conditions than another, we might potentially allow the functional form of the model to look differently depending on which output regime we are in. So for example, let's say we are trying to predict the amount of rainfall. We might think that the model that predicts precipitation in low precipitation scenarios is quite different than a model that predicts precipitation in high precipitation scenarios. That would be an example of a regime. So if you have zeros in time series rainfall data sets, you can still calculate correlation because zeros is another value. Normally you don't do that. Normally you do something like so-called you can. In most software, you can just say ignore the zeros, for example, to practically do that. But you really wouldn't want to do that. Yeah, you would want the so-called two-stage model, where the first modeling stage you model if it rains in the first place, and then condition on that we have some rain, and then do the whole analysis on that. What's more important, model accuracy or model performance? That depends on what you want. That goes back to the question, whether you're interested in prediction or inference. When should we use classification over regression? Again, that goes back to classification you want to use if your output is qualitative. So is it a yes or no, occurring or not occurring, class 1, 2, 3. Regression is if your output is numerical. Yeah, so there's a whole story about reducible versus irreducible error to bias variance trade-off. So in the strict formulation, irreducible error is nothing we can do something about. So irreducible error is an inherent bias in the data. Sorry, this is so fast here. I'm sorry, I think I have to go back to the presentation, and maybe I can take some of these questions here after our next break. Let's go. Thanks for all the great questions here. All right, so now we'll go into some forms of F, more details about cross validation, which I saw you had a lot of questions on in the first half, and model selection. So just a quick reminder here. So now we have this fairly simple model here that we just use all the time conceptually to think about this. So our goal is now we want to estimate that function, and we call it F hat, just as a reminder. That just means we want to get an estimate for it. And our goal here is we want to estimate that F hat in such a way that our predicted value Y is very close to the true Y for all XY. So what we mean by that is we don't just want the model to be really good, let's say at the upper right tail. We want the model to be good everywhere where the model is supported. And when we talk about model supported, that refers to what is the range of Y and what's the range of the X's that we deal with. That fits a little bit back to what David was talking about earlier. You want, when you train these models, you want to make sure that you have good coverage. Yeah? So we have actually X values and Y values available through the entire domain that we are interested in, or at least you need to be aware of that. If you don't, that this could be problematic. So obviously there's literally hundreds of different models we could use for this F here. And we cannot possibly talk about all of them, but it's helpful to abstract it away and think about how we can classify these methods on a high level. And the first thing we're going to talk about are parametric. That means we assume a specific functional form, or non-parametric models. I'm going to talk about this here now. When we have a parametric model, then we need to use the so-called two-step approach. And the first step we do is we state our assumptions about the functional form. A very simple example that you see here is a linear model. So now we specify our function that relates the inputs to the outputs through a linear formulation. So all these betas you see here, these are parameters now in the model, but you can also call them coefficients. So that beta 0 is just a mean term, and then you have parameters that multiply, in this case, they multiply how the inputs relate to the outputs, and the whole structural form is additive. This is about the simplest model you can think of. A deep learning model falls in that same type of category of models. It's also a parametric model, just the specification of what these parameters are and what the functional form is much more complicated. And we can incorporate a lot of non-linearities that makes these models so flexible and really powerful. So keeping that in mind, though, is that in the large categorization, these are still parametric models. That means we prescribe what the functional form is and then just estimate the parameters. The second step is that we use to actually do the estimation. So in the first step, we specify the functional form and what the parameters are. And in the second step, we actually use training data to estimate what these parameters are. And this step can be numerically very challenging. For example, in deep learning, I think the real breakthrough was backfitting algorithms and this type of methodology that actually allows people to practically do this, and where you need a lot of computational power. In some very simple cases, there are actually explicit solutions, such as least squares. That means we have a mathematical solution that gives us immediately what are these values, in this case, in this linear regression model, what are these values for these betas here. So keeping this in mind, the other class of models are so-called non-parametric methods. So in this case, we don't make an explicit assumption about the functional form of F. The reason we would want to do something like that is if we have no clue how the data are related, especially in the exploratory stage, this can be very powerful because we don't impose anything that forces the data to fit a certain specific function. So what we do instead is we look for an estimate of F that is close to the data, but also conforms some other smoothness constraint. Obviously, if we just have an estimate of F that's close to the data, we would have all the F's just go through it. So on high level here is the main advantage of using these non-parametric methods is that we don't impose that specific functional form, which might be far away from what the true functional relationship is. Especially in linear models, for many of the applications that you work with, there are probably extreme non-linearities happening. So just using a linear model would be a very strong restriction of what you could possibly learn a model from the data. The disadvantage of this type of modeling approaches is that you need a lot of observations to actually get a good estimate of what F looks like. Because we don't impose a structural form, we really need the data to estimate what that surface, or in our example, we'll use a surface, but you can think about that analogous in much higher dimensional space here. And then the other thing you need to do is in this setup, you need to weigh how much weight do you give to the fit to the data compared to the smoothing constraints here. We'll look at some plots here, which will make this a little bit more clear here. So what you see on the left-hand side is an example now where we still, our output variable is income. How much money does someone make? And now we have that as a function of two inputs. Again, this is an artificial example to illustrate the ideas here. So the blue surface is the true surface that we are after. And you can see these two variables, that our input variables are years of education, and now we have another term, seniority, how long somebody was in his or her job here. And you can see the red points are the samples we get. And there are still slight deviations here. Again, these black lines here are the so-called irreducible error. There's just some noise around the data that even though we know what the true relationship is, there's some inherent variability between people. What you see on the right-hand side now is that we are fitting a parametric model. And that model we're specifically fitting is a linear parametric model. Again, that's about the simplest model you can think of fitting here. So all we estimate in that model is, in a linear way, how do the years of education and the seniority go into this plot? There's no interaction, that's it, linear model here. You can see there's some error to, again, the black vertical lines show the error, how much is our data away from that surface that's fitted. Now we approach this problem through a specific non-parametric model. The specific one we look here at is a so-called thin plate spline. That's an analogous idea of a smoothing spline in a 1D environment for 2Ds. The details don't matter for that, but conceptually you see now we allow that surface to take on any shape it wants. We're just regulating, we are giving the constraint that we say you have to be smooth surface. That means we tell the surface, and the way you usually impose smoothness is through constraints on the second derivatives. That means you need to have a function that actually has a second derivative. I won't go into any details here, but I think you see the idea here. If you look carefully, you can see that surface is a little bit closer to what our samples look like, but there's still slight deviations here from where the data lies. So not all the data points lie exactly on the surface because we have that smoothness requirement in there. If you look now at comparing two different smoothness assumptions, so the plots we're looking at are both using this non-parametric model, but on the right-hand side, we allow the data to completely dominate. So we make the smoothness constraint really small. We say what we really care about is that the data fits really well. And what you can see here is we get a very wiggly surface. And that's a classical case of very likely we are overfitting here. We have no error at all in our residuals, but we're dealing here in our training data, but very likely we have actually started to fit to the noise here. So that's the illustration of that. And now we'll go into something that you have already touched upon earlier, gross validation. So gross validation, what you were talking about, what DJ was talking about before about validation and test data sets, gross validation is the same idea as that, except it's a bit more of a formal way to be, you could say, organized how you split the training data into test data. So the training data is used to test the model, and the validation, it's used to train the model, and the test or validation data is to evaluate its performance on new data. And what has been talked before, you have to be really careful to keep the test data away so there's no information leakage in any way here. We don't just want to use the training data exactly because of the problem of overfitting. If we just use the training data to evaluate our model, a more flexible approach would always be better, equivalent or better. So when you think about evaluating how well your model fits to your training data, you want to think about that as a necessary but not sufficient condition. So what we mean by that is, if your model doesn't even fit the training data very well, you're probably dead in the water. So you probably want to take that's probably not the right framework. Let's say if even on the training data, your model isn't flexible enough that you get close match to with what your true values are, then you probably want to look further. But if your model fits the training data very well, that's not a guarantee that it will also perform well on the validation data. So that's what we call here the performance on the new data, on the test data, the so-called litmus test that tells you, should you really do this? We'll show a visual example for that here in a second. Cross-validation in general is very versatile. You can use that in a wide variety of settings to evaluate models or find parameters. For example, that whole discussion about hyperparameters, you can use cross-validation to find out what would be your best hyperparameter. Let me give you an example here. Let's look at this in somewhat a bit of detail here. So on the left-hand side, what you see here, the black curve is the true functional relationship between these x's and the y's. All the circles, the black yellow circles, is the data we observe. Again, there's a difference between the black curve and the black circles because there's some amount of noise in your data, like it will be in your practical data, that is the so-called irreducible error. And now you're on the quest. You test 3 different models here and you look how they perform. We have the yellow model, that's a linear model. That's just a straight line here. Then we have the blue model, that's a somewhat lower order, that light blue model, polynomial fit. And then we have the green line, that's a very flexible model. Now, without going into any details, that's like a model where we allow it to fit the data in a very flexible fashion. When you look at the right-hand side here, what you see in that chart is on the left, we see a measure of how well your model fits to the data, so-called mean squared error. There are other measures like root mean squared error, absolute error, but for right now, we'll look at mean squared error. That's the difference between your estimated data and the true data. And on the x-axis, we see the flexibility. That's a proxy measure of how flexible your model is. So you can see the green model here, that's much more flexible, is on the very right end of that scale. And the 2 lines here, the red line is the behavior of your model on that test or validation data, versus the gray line is the behavior on your model on your training data. And so let's look, if we look at the 2 markers here that are the yellow rectangles, you can see that they correspond to the linear model on the left-hand figure. You can see here, so the linear model does better on the gray line, like we would expect. So it does better on the training data than it does on the test data, which is the red line. However, you can see there's still a pretty high error because the functional form of that model just doesn't do a very good job, because clearly we have something going on here that goes beyond a strict linear model. In the blue model, which is a model that's probably from a functional form perspective, very close to what the functional form of the true model is, we can still see that there's a bit of a difference between how it performs in the test data versus the training data, but that difference is somewhat small because we still have a restriction imposed on what the form of that model is. That dashed line here is the amount of noise added. So you can think about that. That is a bound. Your model on new data can't get any better than that. By chance, of course, you could be falling below this line, but theoretically, this is as good as you can get. So the dashed line here at 1, that's in this artificial example, the noise we add that corresponds to the irreducible error. If you look at the green square there now you can see a very interesting effect. So we have a very flexible model. If all you looked at is the gray line, you would say, wow, this is a great model. But if you look at that model in a setting where you use it on test or validation data, you can see that the mean square error actually goes up again. That means if you try out that model that clearly has started to fit noise and we try to fit it to new data, it will not perform as well. All right, so that's some explanation here how we even think about test and training error and keeping that in mind. So going to cross-validation, what was being talked about before, splitting your data in validation and data sets is a specific example of cross-validation, maybe in a less structured way. The two main flavors of cross-validation are so-called leave one out cross-validation. That means you leave out a single observation from from your data set. That observation becomes the validation data set, and the remainder of the data is used for training. And you do that over the entire data set. This can obviously be computationally very expensive. And in many cases, this would be highly impractical. Let's say you run a deep learning model and you have 9 million observations. You would not want to do that. So in these cases, you do something called k-fold cross-validation. What you do there is that the data is randomly split into k groups. So let's say you do 5-fold cross-validation or 10-fold cross-validation. That means we take our data and split it in 5 or 10 groups, and then we take one of these groups, keep that as our validation data, and fit the model using all the other groups here. A lot of questions before were going in that direction. There are many cases where you don't want to do that as a random sample. For example, let's say you're interested in a prediction setting where you're interested in predicting a week out. Then you want to, the data you pull and save as validation data, you want to use a whole week, because it's much harder to predict a week out than if you had data every day before and after. In this specific case, leaving out one day might not be what you are after. Often when you think about defining how you do the specification of what your cross-validation of data look like, you should very much keep in mind what is your purpose of doing the model. And especially in prediction settings, you want to use your cross-validation in this so-called hindcasting way, where you pretend you don't know the data that is similar to what you're trying to predict here. Let me show you two examples here. So these are examples of cross-validations where they were really used to determine a hyperparameter here, using that term again here. And that specific hyperparameter here is the degree of the polynomial. That means we're trying to fit a model and we're thinking, should we use two-order polynomial, second order, third order, and so on. And what you can see here, so there are two examples of cross-validation here. On the left, that was leave one out cross-validation. There we get a single number because we get that cross-validation statistics doing it over the entire data set, leaving one out. And what you can see here, and that's what you hope to find in cross-validation, you can see you have this very distinct, sharp corner here at a degree 2 polynomial. So that's what you find. On the right hand, we're looking at cross-validation where we did 10-fold cross-validation. And here you get more lines because for each of these folds where we leave out the validation data, we get a slightly different value. And one of the questions we saw before in the chat was, how do you know if you have taken enough cross-validation data on how many folds you should do? If you look at this plot here, the findings you have are very similar. If these 10 lines that we see here would be all over the place, you would really want to do more because that would indicate that we get a lot of variability just from the way we sampled. And that's something you can do something about. Whenever you approach something like cross-validation, you want to make sure that your results are not contingent on what is the specific data set I randomly grabbed. So in this case, we would be pretty happy because it'll all behave very similar. All right, with that, I'm going to switch back to some time for questions. All right. let's see here. I think I already answered some of them. Okay, here we go. When using k-fold cross-validation, how do you interpret the varying models for each training set to generate a final model? Yeah. So in that example that we saw, we want to, so we have something we are after. For example, in this case, we are after what is the degree of the polynomial we want to use. So you want to summarize your cross-validation in a way that ideally they would all give you the same result. If one of them gives you that you should use a degree 5 polynomial and the other one gives you should use a degree 2 polynomial, you really want to redo your cross-validation study. So the goal with cross-validation is really that the findings you get, they should all point the same way. That's what have been talking about. You want to get rid of the sample variability. Okay, so some techniques used for k-fold cross-validation, most of the software packages have that automatically built in. So if you fit a model, you can already, for example, in the smoothing spline setting, you can already set up how the cross-validation will work. So, and the question of how large k should be large enough that there's very little variability within your results. So it has to be fitting to what your goal is for the analysis. That's another thing to keep in mind. Is cross-validation important primarily for small data sets? Nope. I would actually say probably cross-validation is more important in more complex data sets. It's pretty difficult. If you have really small data sets, you have a lot of sampling variability from cross-validation. That's probably where it's the least important, only because you can't draw great conclusions from it. Okay, alrighty. Then let's go back through the presentation. DJ, how much time do I have? I'm sorry, I should know this better.
I think you have about, our next break is at 11:20. So
okay.
You have about 8 minutes.
Okay, thank you. Alrighty. So having gone through some of these principles, I'm going to show you an analysis from my grad student, and this is also joint work with Dr. Buchholz from ENCA. William Daniels is a grad student who did all this work. I'm going to give you a practical application here that will get an insight in how to combine all these concepts. So this is a study that's still under the way, so you get to look at things that are not full-fledged, but kind of I'm giving you an insight in how we work about making some of these choices here. So this is all about modeling carbon monoxide in the atmosphere and trying to understand how are these carbon monoxide concentrations related to natural variability in the climate. That's really important so people can predict large burn events which are related. No, I won't go into any of the details here, but I'll lay out to you how you would approach a problem like this. So our response variable here are the CO atmospheric concentrations. And in this specific case, we have 7 regions in the world. They are all in the southern hemisphere. And that's what we think of as our response variables. We'll look at this a little bit more in detail here. This goes back to one of the questions we had before. So here, as a first step, you take out the seasonality because that's not what you're primarily interested in. So once you take out, you model the seasonality and then you work with the residuals. That means you work with what's left over after you got rid of the seasonal component of your signal. And the bottom here, you see these anomalies. That's what we're really.
Dorit, sorry to interrupt. Your screen isn't being shared right now.
Oh no. Thank you.
All right, there we go. Thank you.
Thanks. All right, so going back here, so this is the signal that we are interested in modeling here. So on the top here, you see the actual concentrations, and the bottom you see the anomalies. So the anomalies is what we will use in our supervised regression model here as our output variable. The predictor variable, so this is now the candidate of all the potential variables that might help us explain what the signal looks like here. And you can see these are also in anomaly space. So we have a series of potential candidate predictors, and we're trying to find out what is the best model we can do to explain the functional relationship here. So when you write out this model, this is a form of a linear regression model. It's a bit more complicated model because in this specific model, we use so-called interaction terms. That means the level of one of the predictors can influence the other predictor. That's one example of many possible models you could fit to this. But as an illustration, this is an interesting one here to see that. And specifically, what we are looking at is now we have some variability in these climate indices. And before we have talked about smoothing and ideas that we could use in these types of non-parametric models, that is actually highly important often for using many of your inputs. So that's not something you can only do on your output, you can also use it on your input. And if you think back about that concept between reducible and irreducible error, one of the things we want to do is if we have noisy inputs, which is very often the case in many of our scenarios, we are trying to extract only the signal from these noisy inputs and ideally put a model on this input so we can use that in further modeling what our output will be. So if you look in more detail here, so these are climate indices that many of you might be familiar with, like El Nino or AIO, and you can see these two signals have very different characteristics. So if you're thinking about smoothing these signals, you want to be really aware of what is going on here and how do they differ. And there's some form of subjectivity and subject expert knowledge that goes into making these kinds of choices. For example, what's highlighted here in red, in that red circle, is we have now values that are very close in time. So these are weekly values here of this specific climate index. And what you need to know when you make these choices is, are features like this noise or signal? And that informs how you want to treat smoothing out this signal here. So if we talk about a smoothing kernel, is a specific form of a non-parametric model. You can think about that as an averaging moving window that you put across the data, where you put a specific kernel form. So in a uniform kernel, the kernel would look like this. In a Gaussian kernel, the kernel looks like that. Yeah, the idea is always that the point we're trying to smooth is at the center and gets the most weight. So one of the things we have to evaluate when we do an analysis like that is the window size. And again, the way we determine that is done through cross validation. So here you see what the results looks like using this smoothing kernel here, this with a specific Gaussian smoothing kernel. And you can see that the window size that is determined as a function of doing cross validation looks quite different. So in the Nino signal, that's much smoother, we have a much narrower window, whereas in the AAO case, we have a much wider window here, fitting this. There's an analogous idea, so a different way of smoothing your input signals are so-called smoothing splines. And that's an idea that's analogous to the simplet splines we saw before, but in 1D, where we have a loss function that minimizes two different terms. The first term on the left here is the fit to the data, and the right term here is that the integral of the second square derivative here, and this accounts for how wiggly or how much flexibility we allow in the data here. And again, we have this tuning parameter lambda here that balances the loss and penalty terms. And the tuning parameter is again typically selected with cross validation. And here you can see what the result looks like if you have these smoothing splines here. That looks fairly similar to what the Gaussian kernel is. One approach, if you do something like that, you want to do different approaches and want to make sure that your results are not large, very much different. This is another way of basically sanity checking that what your results will be are not just a function of what methods you choose. Now we can zoom in here, and if you look at that lowest the lowest row here, the AAO, one thing you can see here is that you might be killing some of the signal here. Yeah? So there's clearly something going on here in that signal that might have been lost in our smoothing parameter term here. And here's the last slide we have here. So if you look as a result of what they actually look like in the top scenario, we were doing prediction and testing on a test data set here, and we are actually doing worse than if we hadn't smoothed the data. So this is not the end of the story, but just to give you an illustration of this is another thing you can manipulate is what do you do with your input data? And you want to do some kind of cross-validation testing framework to see what are the effects of doing that. All right, that's it. And now we can really go to last questions.
Thank you, Dorit.
All right. When you do the K group cross-validation, how large should K be? Victor, K should be large enough that we minimize the sampling variability between the different groups. There isn't any more general that typically we use something like 5 to 10 folds. That's the default. But depending on what your data looks like, you want to make sure the sampling variability from the cross-validation is low. What are variable selection methods? Variable selection methods are methods where we include variables. Let's say we start off with only a mean term, and then we include candidate input variables and see how our model behaves. If the model gets better, and there are ways to do that to account for the fact that we have more terms in the model, then we add this variable. If it doesn't get better, we don't do it and we try a new one. This is a very simple way of saying that. There are things such as exhaustive search methods where you try every single combination of the variables. That's computationally intensive, but sometimes the right thing to do. There are methods where you add one at a time and kick one out at a time and look how the model looks. Can you please repeat the difference between inference and prediction? Yes. Prediction means if we get a new set of input variables, we are interested in what is the output. Inference is we want to understand what is the relationship between the inputs and the outputs. We're not interested in if we get a new X. How do you measure model flexibility? Great question. Model flexibility refers to how many parameters are we estimating. There is a concept in statistics called degrees of freedom, and even more so, there's a concept called effective degrees of freedom. So effective degrees of freedom refers to how many parameters are we truly estimating. For example, in non-parametric models, we would be estimating as many parameters as we have data points in smoothing splines, let's say, but because we add that constraint that we needed to be not too wiggly, we actually decreasing the amount, the degrees of freedom. That's why there's a concept of effective degrees of freedom. If you had a linear regression model where you only have 2 input parameters, so you have that beta 0 term, which is your mean term, and beta 1 and beta 2, there you would have 3 degrees of freedom. So that would be considered not a very flexible model. Do parametric and non-parametric suffer equally from the curse of dimensionality? Non-parametric models suffer more from the curse of dimensionality. They all do, but non-parametrics can be even worse. To what end do you conclude that the errors left are only irreducible errors? Well, we cannot know that for sure if we don't know the truth, but one way to do that is if you try out, let's say you try out adding more and more and more inputs, and you try a lot of different modeling approaches, and you still have some error that you don't get rid of. So that is usually an indication that we have kind of reached how well we can model this. In your last example, the leave one out, cross validation left, why is there only one CV value? Shouldn't there be n CV values? No, there's only one CV value because we average. So we leave one out. Let's say we have 100 data points. For each data point, we get an error, but we take that average over the entire data set. So we get only one value. So how can we know how much of the error is irreducible? Is it possible to know that in advance somehow? Yeah, there are some ways. For example, let's say you had that example I was giving with running the climate model. If you run the climate model where you have the same forcing, that means you always increase, let's say, CO2 concentrations by a certain amount, and then you just do these very, very small perturbations, and you get a range of output scenarios for temperature. So in that case, you can actually get some sense for what is already the inherent variability in the data. In other settings, for example, if you take repeat measurements, that's another way to get, even though the property hasn't changed, it's another way to get a first idea of that. Do you have a recommendation about which smoothing kernel to use? Extremely dependent on the data. So one thing to keep in mind is some smoothing kernels are much more local. For example, these Gaussian kernels, they're really local. Versus smoothing splines, they look at the whole data set. So if you believe that your data might behave very differently in different parts of your data series, then you would want to use one that's more local. That's a general rule. How robust would sorry, I lost this. Okay. What are the typical smoothing kernels the Earth system science community uses? I think all of them. I think the most common one is the simple moving average, because that's easy to explain. But these Gaussian kernels, and I think even smoothing splines, is fairly, in the more sophisticated analysis community, common. I am gonna dodge that question on weather prediction and have somebody else answer it, because I don't know much about this. Does cross-validation include any comparisons with independent true measurements to find the true RMSE? Well, the whole idea of cross-validation, yeah, so the whole idea, if I don't know what you mean by independent, but the whole idea is cross-validation only takes the measure on data in the validation data set that isn't included. Alrighty, so I think in the interest of time, I better stop here. Thank you very much, everyone.
Thank you, Dorit.